Welcome to this explainer. Today, we're diving straight into the physics of motion, and we're going to solve a pretty classic mystery without using a single complex mathematical equation. I mean it, no heavy calculus today. If you've ever felt totally bogged down by the math of moving objects, you are exactly in the right place. We're going to rely entirely on clear visual concepts to figure out exactly how motion works. All right, let's just jump right in.
Section 1. Zero average velocity and the mystery behind it. So we constantly use the words speed and velocity like they mean the exact same thing, right? But in physics, mixing them up creates a pretty mind-bending scenario. The legendary MIT physicist Walter Lewin actually poses this exact riddle. Imagine you go on a really long trip, and you're moving fast, let's say you're cruising at an average speed of 100 meters per second. But if you return to your exact starting point at the end of that trip, your average velocity is absolutely zero, literally zero. How is that even physically possible when you are moving so incredibly fast the whole time?
Well, this beautifully highlights the core difference between these two concepts. See, average speed only cares about the total ground you covered. It's kind of like your car's odometer. It just keeps ticking upward no matter which way you turn. But average velocity, it only cares about your total displacement, which is just the straight line distance between your starting point and your ending point. So, if you start and end at the exact same spot, your displacement is just zero. And if you divide that zero by any amount of time, your average velocity is zero. It's completely blind to the actual journey you took.
Which brings us to Section 2, instantaneous velocity, using no complex formulas. Because average velocity really just looks at the massive, big picture, we kind of need a way to figure out what's happening during the actual trip. Enter instantaneous velocity. Think of it like glancing down at your car's speedometer at one totally random split second. It tells you exactly what is happening right now, the exact speed and direction, completely regardless of where you started, where you're going, or the rest of the trip. It's basically the reality of the present moment. But how do we find that exact number without doing a bunch of painful calculus?
Section 3. The secret is the slope and how to read motion graphs. Okay, instead of dense math, we're going to use a simple visual trick. If we graph an object's position over time, the actual shape of the line reveals everything. Take a look at the triangle tucked under the curve here. The bottom represents a chunk of time, and the vertical side represents the distance traveled in that time. Now, to find the average velocity, you just draw a straight line between those 2 points. Simple enough. But we want the instantaneous velocity, right? That one specific moment. So imagine taking that horizontal time gap and just shrinking it. We shrink it closer and closer and closer to zero until it's literally just a single point. When we do that, the line just barely touches the curve. It becomes a perfectly straight tangent line.
So the absolutely crucial takeaway here, straight out of the physics textbooks, is that instantaneous velocity is quite literally just the slope of that line. That's it. We can completely bypass the complex math and just look at how steep the hill or slope is on our graph. If you can visually judge how steep a line is, you can judge instantaneous velocity. It's really that straightforward.
Moving right along to Section 4, stops and fast dashes, reading graph slopes.
Once you know that steepness equals velocity, it gives you this almost superpower-like ability to read these graphs like a detective's cheat sheet. Let's break it down. A perfectly flat horizontal line, that means zero steepness, which translates to zero velocity. The object is completely stopped. A steep upward line, that means fast movement. The steeper the climb, the faster it's going forward. But what if the line peaks and actually starts sloping downwards? Well, that means you're traveling backward, returning towards your start. In physics, we just call that a negative velocity.
To really see how violently these slopes can flip in the real world, let's look at another awesome example from Professor Lewin. Imagine taking a really bouncy tennis ball and just dropping it straight down onto a hard floor. What exactly does the velocity look like at the exact moment of impact?
Okay, so the ball falls and hits the ground moving in a negative direction. Let's say it has a negative velocity of 5 meters per second. But it's a bouncy tennis ball, so it instantly rebounds upward with a positive velocity of 5 meters per second. On our graph, the slope doesn't just gradually, gently change, it violently and instantly reverses direction in a fraction of a second. It literally goes from a steep downward slope to a steep upward slope almost immediately. And this actually brilliantly illustrates a much more dangerous concept, as Walter Lewin notes when talking about a specific scene in a Sherlock Holmes movie, where a man falls and hits a marble floor, and Holmes observes that he crushed his skull. Well, why? The man might have actually fallen at a relatively modest velocity, but the floor is perfectly hard, meaning the time it takes to stop is microscopic.
That sudden razor-sharp change in slope on our graph, going from a falling velocity to a dead stop instantly, means a massive, enormous acceleration. And that incredible spike in acceleration is exactly what breaks things, whether it's an egg, a tomato, or, a skull.
Finally, Section 5. 2 views on motion. Let's summarize.
Let's bring all this together to see how it builds a complete picture. Average velocity tells us the story of the entire journey. It's the big picture summary, right? It draws a straight, simple line from where you woke up to where you went to sleep. Instantaneous velocity, on the other hand, is the exact steepness of the slope at any given single second. It's the raw reality of the now, completely independent of the past or the future.
So, I'll leave you with this thought. Next time you pause at a crosswalk, or maybe you sprint to catch a bus, or you suddenly turn around because you realized you forgot your keys, I want you to imagine the graph of your day. Think about the perfectly flat lines of your stops, the steep lines of your dashes, and the reversing slopes of your mistakes. You are constantly drawing a geometric masterpiece of motion. So, what does your graph look like right now? Thanks for joining me on this explainer.